So this is ECE 343 Signals and Systems. We're in the first chapter and it's the second lecture. Um, Last time we talked about signal classifications such as energy and power. We also talked about various operations such as operations on the independent and dependent variables. Today, we're going to continue our discussion of signals. We'll do some more signal classifications as well as some useful signal models. The first set of classifications I'd like to talk about are continuous time versus discrete time. This pair of descriptions are mutually exclusive, so a signal can either be continuous time or it can be discrete time. It can't be both. Continuous time and discrete time really refer to whether a function or a signal is defined for a continuum of the independent variable or just discrete values of the independent variable. So continuous time and discrete time have to do with whether the independent variable, usually time, is classified on a continuum or on a discrete set. We can also look at what happens with the amplitude or the dependent variable of a signal as well. That can be defined on a continuum of values or on a discrete set of points. And that's what brings us to this signal classification of analog versus digital. An analog signal has an amplitude that can come across a continuum of values. A digital signal can only occupy discrete levels of amplitude. It's a quantization process that would be typical of an A to D converter on a computer, for example. I would point out that continuous time and discrete time are different than analog and digital. In a lot of literature, these two terms are confused or they are used interchangeably, but they're really not the same thing. I think part of the reason this confusion comes around is because continuous time signals often occur also being analog. So continuous time and analog oftentimes come together. And in the same way, discrete time and digital oftentimes come together. They don't have to, but they often do. And it's probably that common association of those pairs that those two terms end up getting interchanged with one another. In this particular class, we are going to make high use of the continuous time and discrete time signal classification. This is an important classification for us. In fact, entire chapters of the book are separated based on whether a signal is continuous time or discrete time. And that really highlights one of the reasons why these signal classifications are so useful and so important. If we know whether a signal is continuous time or we know whether a signal is discrete time, it points us to the right kind of math to use in order to manipulate or otherwise work with that signal. In this particular class, we're almost always going to assume that the amplitude is defined on a continuum of values. So we're going to assume the underlying signal is analog. This probably is not reflective of reality when it comes to signals on a computer, but it turns out that discretization of amplitude is a rather difficult process to handle in its mathematical completeness. It's a nonlinear, lossy operation when we discretize the amplitude of a signal, and it's just one that's not really suitable for an introductory signals class. In most applications, when we go to a discrete time signal and we quantize the amplitude, we use enough levels in the amplitude that you don't notice terribly that discretization in amplitude. So assuming that everything is being analog, that it can have basically any amplitude value that you can dream up is not a bad assumption in most cases. I have a set of graphs that help kind of illustrate these concepts of continuous time versus discrete time and also whether something's analog or digital. So on this side here, I'm looking at a signal being classified as either continuous time or discrete time. And on the horizontal here, I'm looking at whether things are analog or digital. If we focus on this first graph here, right? This first graph has a signal that is both continuous time and analog. What does the continuous time mean? It means that any value of that time variable or the horizontal axis has a corresponding value of the function. So you will see the function is defined or shows a value in amplitude on any of those values along the entire continuum going minus infinity to infinity. The analog part means that the amplitude can take any of a continuum of values on the vertical axis. And what you get is a very smooth looking signal, right? That is smooth in going from left to right and also smooth in going from up to down. If I go just below that, we're going to take a look at the other signal type that we're going to consider a lot in this class, and that is a discrete time signal that is also analog. The discrete time now says what? It says that we're only going to define the signal at discrete instances in time. So as I go along that horizontal axis, right, I see that there are values at, let's say, some sample at the origin, that's the first sample, and then another unit over to the right, and another unit over to the right, and another unit over to the right, maybe the same thing off to the left. So I got discrete instances where that guy is defined. If I look between those samples, something over that interval that I've just done with an arrow, the signal has no definition. We don't define it. We don't consider what it is. The fact that we've got gaps in our data as we go along from left to right along the horizontal axis along the independent variable is a thing that is indicative of this being discrete time. The amplitude can take any of a continuum of amplitude values. So that part, any amplitude you dream up is something that we could represent. If we go up to digital and continuous time still means I've got a value for my function anytime I go along that horizontal axis. As I go along this, and I've drawn the kind of, maybe you would think, an underlying waveform in black, and then the red is the signal that is actually the continuous time digital. Any value of the time variable, the horizontal variable, right? You get a value of the dependent function, the dependent variable. What doesn't happen is that the amplitude is not allowed to take any value. In this particular case, I've exaggerated it. It's a pretty low quality amplitude representation. I'm using something that is similar to a single bit. It's basically going to say, is that signal on the plus side of things or is it on the negative side of things? So if I take a look at those amplitudes, right, anytime that the underlying waveform is positive, I just am going to cap that guy out at a flat value, right? That's one level. And anytime the signal was negative, I'm going to cap that thing out at some negative value. So that sinusoid underlying becomes something that looks a bit like a square wave. So that quantization of the amplitude, the thing that makes it digital in this case, does distort the waveform, and it can cause some signal degradation or loss. If I go to the final case, this is the one that is both digital and discrete time. I go along the horizontal axis and we see that the waveform is only defined at discrete instances in time. And we also see that going along the vertical axis, this again is capped at a fixed number of amplitudes. In this particular case, I've got two amplitudes that can be represented, right? Corresponding to a 1-bit representation of the amplitude, and the waveform has obviously got some restrictions on that. These are the 4 different basic types that come out of these 2 different signal classifications as to whether we are continuous or discrete on both the independent and the dependent variables. As I had said before, we are almost exclusively in this class going to consider the case of an analog continuous time signal and also an analog discrete time signal. Those are the ones we're going to spend the most time with. The math in dealing with a continuous time signal is generally different than the math involved in doing a discrete time signal. Consider the following example. If I wanted to find the area of that continuous time signal in the upper left, that would be pretty easy. I could do some sort of integration and it would give me all these areas all added up. So you could define an operation of integration to give you the accumulated area of that waveform. If I wanted to try to do that for the lower left, the discrete time analog waveform, I wouldn't have much luck being able to do that because I just have isolated points, and those isolated points don't have any integral area. Integration would not be an appropriate math technique in dealing with that discrete time analog signal. Instead, what would we do? We would carry out that accumulated area through just a physical sum. So we just add up the point values. It's a very similar kind of operation. It still gives us an idea of how much total signal there is. It's just that the math behind it is different, summation instead of integration. Let's also take a look at a signal classification about whether signals are even or odd. These are symmetry kinds of arguments here, and we'll just do it definitionally. An even signal is a signal that is equal to its own reflection. So if a signal is equal to its own reflection, we would call it even. It's an even signal, and sometimes we'll indicate that through a subscripted e on the waveform. So xe of t equaling xe of minus t. The signal satisfies the definition for evenness, that it's equal to its own reflection, and we put the e down there just to remind us that indeed we're talking about an even signal. Evenness or oddness are statements of symmetry. If I know a signal is even, right, I only really need to know it for positive time, and I get all this stuff for negative time for free. So for example, suppose I said that x was an even signal, and I showed you that at least for positive time it looked like that. I wouldn't have to give you the negative time. You get it for free by knowing the symmetry. I could sit there and say, oh, I know it has to be mirror image symmetric, so it's going to just go back in a mirror image way, right? Because I knew about this symmetry problem, that it was an even function. An odd function is similar. It is antisymmetric about t equaling 0. We can state that mathematically as x odd of t is equal to the negative of its reflection. And so again, we could play the same sort of game. This is extra information. You only have to maybe deal with half of the signal in order to fully understand it. So if I gave you the same looking waveform, right, and I said, okay, here I've got something that looks like a cosine for positive time, but I told you it was an antisymmetric or an odd signal, well, then you would easily be able to get the other side of that, even if I hadn't given it to you, because you would just do the negative reflection of that guy. So in this case, it would look something like that, right? So we would just getting it go to the negative value as you move from 0 off to infinity negative. For an arbitrary signal, x of t, so we're going to look at any old signal. It doesn't have to have any symmetry built into it. We can notice a few things. If I take a signal, x of t, and I add to it its reflection and divide by 2, this whole definition has built-in evenness. That necessarily is equal to its own reflection. So if I take a signal, add to it its reflection, and divide by 2, and I just call it something, then I'm going to call it xe of t because I know it satisfies the property of evenness. I can get an even signal from my arbitrary signal, right? Just by adding a signal to its reflection. I can do the same sort of thing. I can build a definition to get an odd signal. So I can take a signal minus its reflection, divide by 2, and that has built-in oddness. Now, something interesting happens when I add these two guys up together. When I take this x even of t and this x odd of t and I add them together, take a look at what happens. I have x of t plus x of t, both divided by 2. So x of t over 2 plus x of t over 2 does give me x of t. I've shown that down there. The x of minus t plus a minus x of minus t, those guys will cancel. So if I add these two pieces up together, what I'm left with on the left-hand side is just x of t, and on the right-hand side, I just get the even part plus the odd part. What does this tell us? Any signal can be decomposed into a sum of an even signal and an odd signal. Stated a little bit different way, you could say any signal, right, has both an underlying even part and an odd part. Let's do a very quick example just off here in the margin. So I'm going to take a look at a signal we introduced last time. So I'm going to have this guy be 0 before t equaling 0, and then at t equaling 0 forward, we're going to go ahead and show it as being a 1. This was the unit step function, something like that. If I wanted to find the even part of this signal, what would I do? I would take this signal plus its reflection and divide by 2. Let's assume that unit step, as per definition, has an amplitude 1. If I take that signal plus its reflection, I'm going to have something that points to the right and to the left both, and then I'm going to divide it by 2. That means everything to the right is going to have a height 1/2, and everything to the left is going to have 1/2 as height as well. And I guess if we were going to get really picky and look at what happened at the origin, you would have a value of 1, something along those lines. Now, if I wanted the odd part, same definition, right? Except for instead of taking the signal divided by 2 plus its reflection divided by 2, I'm going to take the signal divided by 2. There it is. Take the signal divided by 2. There's the unit step divided by 2, so it has a height 1/2. And I'm going to add to it its negative reflection. So that's going to look something like this. It's going to have a height minus 1/2. And so you can take a look at both of these guys, and it's 0 at that point of discontinuity, just to be absolutely accurate in this case. If we take a look at these guys, so this is my x even, and then I have my x odd. Clearly, x even has even symmetry, right? It's got a mirror image symmetry about the origin. If I look at x odd, what goes off on to the right is mirror imaged off to the left. So both of these clearly, we can see graphically, fit the definitions of evenness and oddness as being symmetric or antisymmetric about the origin. And when I add them together, when I take x even plus x odd and see what happens, 1/2 plus 1/2 gives me that 1, and that's true for all positive time. I get minus 1/2 and 1/2 added together, that gives me 0 for all negative time. And then at 0, I had a point of 1 and 0, and that ends up giving me that 1 that I originally had. So we can see how we can recover this original signal that was neither even nor odd by looking at two pieces that were both even and odd. These kind of decompositions crop up every once in a while, and they also find their way when we start taking a look at certain types of operations or certain types of transforms. These kind of symmetries naturally come out, and it's useful to exploit or take advantage of these symmetries. I'll give an example of that in a minute. Even and odd is one way to do it. A useful extension of this, and probably one that would be more relevant to this class, is one that is set up a little bit more intentionally for complex signals or signals that might be complex. And so we're going to introduce this idea of a conjugate symmetric signal. A conjugate symmetric signal is one where the signal is equal to the conjugate of its own reflection. It kind of looks like a bit like our even definition, but I've just got that conjugation in there as well. If I broke up my signal x into a real and imaginary part, what I would find out is that this means that the even part of my signal has to be real, and the odd part of my, or the imaginary part of my signal has to be odd. So the real part of my signal is even, and the imaginary part of my signal is odd if I have a conjugate symmetric signal. In a similar way, I can talk about something being conjugate antisymmetric. This is a bit like the odd definition. I just got that extra conjugation in there. A conjugate antisymmetric signal is odd in the real parts and it's even in the imaginary parts. Again, you can see this just by putting in a rectangular form for my signal x of t. If I look at an arbitrary signal x of t, just like I did for the even odd decomposition, what I can find out is that I can take a signal plus its conjugate reflection divided by 2, and that naturally has built-in conjugate symmetric symmetry. And so I will just call that component conjugate symmetric part of x. I can do a similar thing. I can take a signal subtracting its conjugate reflection divided by 2. That has built-in conjugate antisymmetry built into it, and I'm just going to therefore call that part conjugate antisymmetric part of x. If I add these two together, much like I did before, what I find is the left-hand side simplifies to just the signal x of t, and what we get on the right hand is the addition of the conjugate symmetric and conjugate antisymmetric parts. So very similar to what we did for an even-odd decomposition. This one just a little more suitable for functions that could be complex. They don't have to be. You can also apply this to real signals. And it just says that any old signal can be decomposed into a sum of conjugate symmetric signals plus a conjugate antisymmetric signal. Why might this be useful, or how might we use it in this class? Well, later on in the semester, we're going to be talking Fourier analysis. A really common thing for us as engineers is to deal with a time domain signal that happens to be real. When we have a real time domain signal and we transform it using the Fourier transform or Fourier series, some form of Fourier analysis, what we find out is that in the frequency domain, the signal becomes conjugate symmetric. Okay, it satisfies that conjugate symmetry property. So there's some built-in symmetries, and that cuts in half the amount of stuff that we have to compute or store. And it also is a way of catching errors. If you go through some analysis, some Fourier analysis on a signal that was real in the time domain, and you don't get a conjugate symmetric signal as your result, then you know you made an error somewhere. So we'll see this guy crop up again. Let's next look at this idea of periodic and aperiodic. I'm going to switch my lecture now to where I'm spending a little more time just writing things out. So a periodic signal, as I think many of you have seen before, is a signal that repeats itself with some period. Let's go ahead and call that period cap t, or we could even call it t naught, for all time. So we need that repetition. So there needs to be a repeating pattern in the signal, and it needs to repeat for all time. A word definition like I've given here, something that I've written out as a sentence, is certainly fine, but it's certainly a lot better if I can capture this idea, this property, this definition in a mathematical sense. I'm going to go ahead and do this initially for a continuous time signal. So a signal x of t is periodic if what? The signal is equal to itself shifted by that period. We could say minus t or minus t naught. So if a signal is equal or not distinguishable from itself when it's been shifted by that period, and that has to be true for all t. So that sort of v with a line through it is read mathematically as for all. This overall statement says what? A signal is indistinguishable, or the same as the signal shifted by some fixed amount t naught for all t. If you can't tell the difference between the signal and its shift, then it is indeed periodic. Then we can say this guy is periodic. If there is no cap t naught, for which this is true, then it would be an aperiodic or a not periodic signal, something along those lines. So I think everybody's seen stuff like a cosine as an example. So we could have something like a cosine t. And so we have this signal that does our sinusoidal oscillations, and those guys go on for infinity. I'm going to, for the fun of it, just highlight that point at the origin. And I'm going to go ahead and think of this guy as being a cosine t. And so I know this first peak coming up here occurs at time t equaling 2 pi. If I looked at cosine of t minus 2 pi, what would it look like? It would look identical. It would still be the sinusoidal looking piece, right? It would look exactly the same as what we had on the left. Those guys are totally equivalent. If I track, though, that point that I had identified originally at the origin, it would have been over here. That's that indication of that shift going on. So we shifted the waveform, but yet by all visual appearances, they look the same. We therefore know that cosine t is a periodic signal. So this is periodic. It is periodic because I can see that it's equal to its own shift, right? And I can see that its period is cap t naught equaling 2 pi. There are other values of T naught that would work in here. We could also have put in here 4 pi. That would have made that point track over there here to 4 pi. It would still satisfy this definition of periodicity. It's just not the smallest value of T. Usually we give the smallest value of T. That's called the fundamental period. So T naught, the smallest one, the smallest that works for that is called the fundamental period. Fundamental period, but it also turns out that any integer multiple of that fundamental period is also a period. Usually we just stick with the fundamental. And so in this particular case, the fundamental was 2 pi. Let's also take a look at what would be considered a definition for periodicity if I was with a discrete time signal. We had indicated before that a discrete time signal, we were going to help kind of highlight the fact that it was discrete by using square brackets instead of curved parentheses, and that our time variable was going to be an n instead of a t. We still need that signal to be equal to a shift of itself. So it still has to be equal to some n plus some cap n. We could call it cap n or cap n naught. I'll call it cap n naught for this particular time. And that has to be true for all values of the independent variable n, right? Something along those lines. Definition looks very similar. It seems to be in many ways just a very, kind of a superficial change from what we saw for continuous time. I'm just using those square brackets, right, to indicate it's discrete. And then I've also got that independent variable labeled as n instead of t. But there is a little more going on in this particular case. And it, I think, again, highlights this idea that sometimes it's a little bit separate math, or maybe it's a little bit of separate thought behind signals at either continuous time or discrete time. So let's take a look at this. What do we know about that n? N is an integer, right? We said that this thing was supposed to be going along at a particular set of discrete sample values. The way the book handles this is it just says we're going to restrict it to be the integer set. So n is an integer. Furthermore, what does it mean? It means that that shift, cap n naught, must also be an integer. Now this doesn't show up necessarily in the definition just as I wrote it, but because we understand the arguments of a discrete time function need to be integers, there's an implied constraint that if this signal is periodic, it has to be periodic within integer shifts, and that can make for some surprising results. Let's take a look at a discrete time signal and see if we can find its period. We'll look at a couple different ones in this particular case. The first one I'm going to look at is going to be some x of n, and let's look at our friend the cosine again. We know as a general function, cosine is a 2 pi periodic function. I'm going to give this one a little bit of a strange frequency. I'm going to go 2 pi by 100 times n, something along those lines. I could certainly generate this waveform. I could put it into MATLAB. I could get a nice plot of it, whatever the case may be. I want to know, is this periodic? Is this a periodic signal? How would I test this out? I need to find out, is x of n equal to x of n plus some cap n for all n? Is that statement true? Let's go ahead and look at x of n plus cap n, plug it into the definition of what we know xn is. That's a cosine of, we had 2 pi over 100, but now the argument is getting changed from n to n plus cap n. And I know this whole thing then is just going to be a cosine of 2 pi over 100 little n plus 2 pi over 100 times cap n. Something like that. And what are we trying to test? We're trying to test, is this equal to cosine of 2 pi over 100 n, right? Which is equal to my x of n. That's the thing we're trying to test. What do I know about a cosine? Cosine as a function is a 2 pi periodic function. That means that, and you know this from trig as well, we know, so back from trig, our study of trig, we know cosine of a plus any integer multiple of 2 pi is equal to cosine of a, right? So as long as this piece over here, 2 pi over 100 times n, can be made into an integer multiple of 2 pi, I'm going to be good to go. So This thing is going to be periodic. It will be periodic. It will simplify down to that just x of n if, right, we have that 2 pi over 100 cap n is being equal to any integer multiple, by choice, any integer multiple of 2 pi. I'm going to do a little bit of work here. I see I have 2 pi on both sides. Those guys will cancel. I'm trying to find out, is there an integer n that this expression would hold true to? Multiply both sides by 100. That says n equals 100k. K is also an integer. We knew that as well. So both of those guys had constraints of being integer. So is there a value n? Well, sure. I can pick any. It's my free choice. Any value of k. K equaling 0 would be kind of boring. That's not going to do us anything. That's not a valid solution for us. But I could pick k equals 1, 2, 3, going on off to whatever. And to get the smallest positive value of n, I would use k equaling 1. So k equaling 1 gives the fundamental. So we see that cap n equals 100 times 1. So cap n equals 100. Cap n equals 100 is the period of our now known to be periodic signal. And we have here, whoops, x of n, right, being equal to cosine 2 pi by 100 n. You could test this pretty easily in MATLAB. You could go ahead and grab MATLAB and tell it to plot out this waveform and then choose n doing something like this. You could go from 0 up to 200. You could pick 200, well, there'd actually be 201 points there, but 200 points, if my period was 100, that should repeat 2 cycles of the waveform. So this is a waveform that takes 100 samples to repeat, right? And exactly 100, no problem. It's kind of like we'd expect. Let's try one more. So let's look at one other example. Let's look at a different signal, x of n being equal to, in this case, cosine of n by 100. It's different from the other one in the fact that there's no 2 pi factor in the numerator. You could plot this out with MATLAB too, and you would see something that looks very cosine, and it would seem to be repeating with a pretty regular kind of pattern. I want to know, though, is this guy periodic? What is required for periodicity? I need to know, is this equal to, so question mark, is this equal to x of n plus some cap n? Put that into my expression. I get a cosine of n plus cap n over 100, which I could write out as being cosine, right, of n by 100 plus cap n by 100. To be able to legitimately ignore this piece, it can go away if that is equal to any integer multiple of 2 pi. So what am I going to test for periodicity? I need to know, is there an n by 100 that equals 2 pi k? I'm going to just write this in a slightly different way. I'm going to take both sides, divide by 2k, okay? So if I divide both sides by 2k, I'm going to get here an n by 200k as being equal to pi. And what does this say? It says that pi, a number that we all know, pi is rational, right? It says that it's a ratio of integers. I could have picked any k I wanted, and I can pick really, or trying to find any n that might satisfy this, but there's no set of integer values n and k that, when taken in a ratio, n over 200k gives me pi. This is a contradiction. This does not hold. Can't be done. This can't be done, right? So what does this mean? This means that x of n is not periodic. It never repeats exactly, right? It can go on forever and never have a repeating sequence. You would always be able to tell if you had shifted this guy. And that's sort of a bit of a surprise given the fact that it comes from an underlying cosine function, and that function itself is known to be periodic, right? The reason it's not coming out periodic is because it's a cosine operating on integer values, and the particular frequency here chosen is such that the ending sequence of values that come out of this never does quite repeat, not exactly, does not fit the definition. That's probably enough of periodicity. Again, you might ask, why does this matter? Why do we care about things like periodicity? So we could sit there and say, why care? Why do we care about whether things are periodic or whether we know? Again, this is something that can point us to the right math. So for example, if a signal, let's do this in a different color, let's just look at a signal x of t. We know it can be a couple of things. It could be periodic, right? or it could be aperiodic. It could be aperiodic. Those are two different choices. They're mutually exclusive, guys. When we later talk about transforms, what we're going to find out is that if I have a periodic continuous time waveform, we are going to look at that guy or analyze it using something called the Fourier series. Fourier series is the appropriate analysis tool for periodic continuous time waveforms. If it's an aperiodic signal, though, Fourier series really isn't the appropriate tool. The appropriate tool is something called the Fourier transform. So for you to be able to successfully take a look at your signal x of t in the frequency domain using Fourier analysis, you do need to know whether it's periodic or aperiodic. So it's a classification, yes, it's something that we got to know and understand. It tells us something about the characteristic of the waveform, in this case, a repeating pattern in it, and it also will point us to the right kind of math in which we can analyze this and work with this signal in the context of signals and systems. There's a lot of other kinds of classifications. I'm not going to spend so much time on these, so let's just say other classifications, other classifications. I think I might do these just by single words and see if we can get through it. So you can talk signals that are either deterministic, right? Deterministic versus random, something like that. So a deterministic signal is one that you can write an expression out and you know what that signal is going to be for all time before it's ever happened, just because you have a closed form known expression for it. A random one has got some uncertainty. It could be one thing one time and another thing another time, and we don't have just a closed form solution for it. A deterministic signal might be something like cosine t, right? The randomness might be some noise that corrupts that deterministic signal. In this class, we are going to be spending time mostly through deterministic signal analysis, and we are not going to do so much with random signal analysis. That's a whole nother kind of class to do, random or probabilistic signal processing, as it is called. So in this particular class, we're going to spend most of our time with deterministic. We'd already talked about, for example, energy versus power classification. So that was a classification we'd seen before. We could have stuff like this. We could have everlasting, right, versus finite duration, okay? So this is another type of classification that we could talk about. What would an everlasting signal be? An everlasting signal might be something like this. It might be a decaying exponential that starts at 0. It doesn't everlasting go to the left, but it does go everlasting to the right. There's not a fixed bound on both its left-hand side and its right-hand side. It has something that goes out to infinity, even if it asymptotically heads to 0. This would be considered an everlasting signal. Mathematically, I could write that something like this, maybe e to the minus t u of t. A finite duration signal is exactly like it sounds. The finite duration indicates a duration in the independent variable support for this, or where it's defined non-zero over a finite interval. I might have something like that signal we had looked at before that was a unit amplitude 2 duration pulse, so -1 to 1 with height 1. This guy would be a finite duration signal. This one here was an everlasting signal, something along those lines. So other ways of classifying signals. Some other ones that we might deal with, there is an idea of causal versus non-causal signals. Causality is something that we're going to take a look at a lot from a signals perspective. It's connected to whether systems can be physically implemented, so it's something that we're going to see coming back again. Let me just give a mathematical definition of causality. A signal is causal, so x of t, right, is causal. It is causal as a signal. This is a signal property. It is a causal signal if x of t equals x of t times u of t. What this means is that the signal must be 0 for all time less than or equal or less than 0, something along those lines. It has to start at 0 and then have its non-zero content go forward of that. Non-causal is anything that doesn't satisfy that. Let's take a look at a couple very quick signals. We'd already seen something like the unit step. So if I looked at the unit step as a function of time and I plot that guy out, right, it is 0. It is 0 for everything to the left of the origin. And as such, because it is 0 to the left of the origin, that is absolutely a causal signal. I could shift that signal to the right by 1 through a delay operation. So I might have something like this. This could be a u of t minus 1 as an example. That starts at 1. Again, this guy is 0 to the left of the origin, and so it is a causal signal. It has started at 0 or later. It doesn't have anything going on before the origin. If I ran this signal, if I, instead of delayed it, I advanced it, and took a look at what that guy looked like, I might do something like this. This is a u of t plus 1. Now we see this guy starting at minus 1. If I look over the negative time, right, this guy has got some non-zero content to the left of the origin. It is not a causal signal. It is a non-causal signal because there's some non-zero content to the left of the origin. You can further see that because if I multiply this guy by a unit step, right, the whole thing ends up looking just like a unit step, which does not look like that left shifted version of it. So pretty easy to test on these guys. There is a related term, not quite the same as non-causal. There is something called an anti-causal signal. I'm not going to make a huge deal about this, but let's just talk about as a definition. A signal is considered an anti-causal signal if the signal is equal to itself multiplied by u of minus t, right? So if it has all of its non-zero content to the left of the origin, right, it's anti-causal. You can be anti-causal and also non-causal, but just because you're non-causal does not mean you're anti-causal. Let's take a very brief look at what we had before. We had that signal right there, right? It was a non-causal signal because it had some stuff to the left of the origin, but it is not an anti-causal signal because it's got some stuff to the right of the origin. An anti-causal signal might be something more like this. We might have a little pulse going here from -3 to -1 with height 1. That would be an anti-causal signal because what? There is nothing over there to the right of the origin. Everything that is non-zero is to the left. Okay, so that's probably enough about non-causal, anti-causal, and causal. There are a few signal models that we should talk about. We'll try to do this to finish out the lecture for today. So let's talk about some useful signal models. We are interested in being able to represent inputs and outputs, for example, signals of interest, and having some signal models to help us do that is certainly useful. We've already seen one. So, for example, just a reminder, recall that we do have this one signal that we've talked about already, the unit step function. The unit step function is 1 for when the argument, in this case t is greater than or equal to 0, and it's 0 for t less than 0, something like that. And if I plotted that guy out, it would look like this: height 1, right, at any time greater than or equal to 0, and it's 0 to the left of that. So we've looked at things like that unit step before. We can do lots of things with just a simple model like that. So for example, if you recall that we had that pulse that we looked at when we were first introducing the idea of the shift operations. So here was a signal x of t, right, as a function of t that had height 1, and it went from -1 to 1. Notice something here. I can construct that signal as being equal to what? I could take a unit step that had been shifted to the left, right, -1, and I could subtract from that a unit step that had been shifted to the right, 1 unit, something like that. If I carry out those two operations, if I take a left shifted unit step and I subtract from it a right shifted unit step, I end up getting that pulse again. So I could write that out mathematically, right? I could say my x of t is equal to a u of t plus 1 minus u of t minus 1. And so what we see with these signal models is that these signal models can give us a kind of a convenient way of decomposing other signals or building up other signals. We can break them down into useful known chunks or chunks that we have better understanding of those particular pieces. There's another particularly useful signal that is going to help us do exactly this kind of operation, decomposing a signal into useful or kind of building block pieces. And this is connected to something called a Dirac delta function. So let's take a look at the Dirac delta function. You might have seen this before in another class. We'll still go through all the details on this. It's a fundamental quantity, especially when we talk about time domain analysis. time domain analysis of signals and systems. And so let's work our way through that. A Dirac delta function notationally, I'm just going to use the Greek character delta, and it is a function of time. So this is a function, something like that. So we're going to denote this function delta t. There are two important properties associated with delta t. So there's going to be two important properties, and we might say defining properties of this delta function of delta t. I will say that the Dirac delta function, it's a little bit of an abuse to call it a regular old function. It's not really a regular function. It's a function with some quirks. We would need to dig in some math to probably fully appreciate it. It falls under a category or a class of signals called generalized functions. And what I'm going to say is that all by itself, delta t has got some problems. It's got some issues standing by itself. Just because it has problems standing by itself doesn't make it not useful. It's very useful for us. We'll see that as we develop some more stuff. But a delta function is not something you could realize with a physical signal. You could not make you could not make this delta t as a voltage, as an example. We'll see that as we get to our couple of properties and we visualize what this particular waveform is. What's the first property it's going to have? Delta t is equal to 0 for all t not equaling to 0. Wow, that's actually a pretty strong statement, right? This is saying that this function is 0 almost everywhere. There's only a single point where this function might be non-zero. So if I take a look at what I'm looking at for this delta function, there's my axis. I know that it's 0 everything to the left, right? I know it's 0 everything to the right. And the only thing I don't know is what happens at the origin. This thing, in some respects, is the most boring function ever, right? Because it's 0. Nothing's happening for almost all eternity. If I look at the second property, though, the second property makes up for that boringness in a big way. The second property on this guy says the following, that the integral of a delta function, right? So integral of delta t dt is equal to 1. This is doubly interesting because we have a function that's 0 almost everywhere except at a single isolated point, and yet it still has area. And really the only way that this can happen is if the delta function goes off to infinity at 0. So there's something about this that this implies that delta t tends off to infinity as t goes to that origin point. To maybe help us visualize this, I'm going to provide a picture that in the limit would satisfy these two properties, and so could be a way of visualizing the delta function. And then we'll indicate why maybe this picture is not complete in describing a delta function. So let's go ahead and take a look at a graph of a function. I'm going to go ahead and look at something that looks a lot like that function we'd seen before of a little pulse. But I'm going to let this pulse, instead of going from -1 to 1, I'm going to have it go from -t to t, okay? And then I'm also going to ensure that it's got a particular height, and I'm going to do that as oops, I didn't want that one. I want to do it as 1 over 2t. So if I take a look at this function, right, and I say, okay, function, what is your area, right? What's the area? What's the area of that function? Area, because it's a rectangle, right, is base times height, which is equal to, the base is 2 cap t wide, and the height is 1 over 2t. Those 2t cancels, and it's 1. So this is a function that regardless of what I choose t to be, it has always got unit area. Well, guess what? That's going to go up to this second property, saying that the area, that's the integral, right? The area of my function has to be 1. This is a function that forces itself. It has, regardless of cap t, its area to be equaling to 1. What am I going to do next? I'm going to look at the case when t goes to 0. So as t goes to 0, what happens to this guy? It gets narrower and narrower and narrower, but then its height has to get taller and taller and taller. As I start squeezing its width smaller and smaller and smaller, the height has to get bigger and bigger in compensation. As t goes to 0, right, the height goes to a limit as t goes to 0 of 1 over 2t, which heads off to infinity. So we can squeeze the width down to nothing, but then the height has to go out to infinity, and it does so in such a way that it preserves the area of being 1. These two properties together, if I take t going out to 0 and I've constructed it as this rectangle function, do satisfy this idea, right, of my delta function, the two properties of that delta function. So you can think of a delta function, right, as 0 almost everywhere, but then at 0, it has tremendous action, right? It flies off to infinity. It has finite area. It's a very impulsive function, which is why they call it an impulse function or a delta function. A lot of times you'll hear the Dirac delta function called the impulse function. It's called an impulse function because it's very impulsive in its character. A way you might think about a good approximation of a delta function is visualize taking a hammer out and then taking a bell out. And if you take that hammer and you whack the bell, what happens? I throw a bunch of energy into the bell and I do so almost instantaneously. That's an impulse, right? It's an impulse input to that bell. There was no input to the bell before I whacked it with the hammer. There's no input to the bell after I've whacked it with the hammer. And it's just in that instantaneous contact between hammer and bell that all that energy gets stuffed into the bell. So this impulse function is pretty interesting. We're going to look at it as kind of our hammer function, a way of whacking systems to stuff energy inside of them. We'll talk more about that as we move along. We can summarize these two properties in a single equation. So we can combine the two properties into a single and useful equation. And this equation has the name, it's called the sifting formula or the sifting property. So I'm going to call it the sifting formula for right now, but you might also call it the sifting property or the sampling formula. So the sifting formula, something like that. What does the sifting formula say? It says that a signal x of t can be represented as an integral minus infinity to infinity of x of tau, and I'm going to have a delta t minus tau d tau. So let's take a look at this. The right-hand side of this expression is basically using a delta function, right? When is that delta function non-zero? This is non-zero when the argument is 0, so it's at t minus tau equaling to 0 or when tau equaling t. So that function is non-zero at tau equaling to t. When tau equals to t, this guy is equal to x of t. It's just a value, and it can be brought outside the integral. And I'm left with x of t integral, right, of delta t minus tau d tau. And I know that the integral of a delta function, right, this integral of a delta function goes to 1, so we're left with just x of t. So if we use our two properties, we can definitely show that this equation holds. This is a different kind of decomposition, and I want to rewrite it out because it's an important one, and I want to think about it in a little bit more of an intuitive way. So let's take a look at that sifting property or that sifting formula one more time. X of t equals an integral minus infinity to infinity, and I'm going to have x of tau delta t minus tau d tau. There's a story behind this formula, much like there's been a story behind some of the other formulas that we've looked at as well. For example, we took a look at a Taylor series. So let's do a very quick aside on that, right? An aside very quickly says something like this. It says a Taylor series, let's redo that. A Taylor series says something like this, that x of t equals some sum of scaled polynomial pieces, polynomial pieces. It was a way of decomposing a function into simpler, useful pieces. This one that we've just dealt with, this sifting property, does something very similar. It says some function, right? Some function is representable. It's equal to. An integral is just a limiting form of sum. So I'm going to write it out as sum. It's just a little more intuitive that way. X of tau, that's not a function of t at this point. It's just a scale factor with respect to the variable t. I know it's within that integral, but it's just a scale factor. So this is going to be some scale factors. So there's some scale factors multiplying some time-varying functions. That's the delta thing. The only thing that's got a t on it in the right-hand side is the delta function. So it's saying our function can be represented as a sum of scaled, right? And then what? We've got shifted deltas, okay? So the sifting property or the sampling property or the sifting formula, all of them the same thing, basically says the following. I can decompose a function into a linear combination, sum of scaled, right, shifted delta functions. That's going to turn out to be very powerful for us in understanding or being able to come up with a mathematical description of input-output behavior of systems. Okay, and so that will be the foundation for us to understand input-output behavior of systems. It's really important that we get familiar and comfortable with this guy. The book does a really nice job of showing this a bit. So we have some sort of waveform. You got that waveform in there. And basically what this sifting property does is it says we can take a bunch of delta functions all stacked together, and it uses some limiting process in there. That's part of that integral part. And if we hook them all together in a continuous sum, an integral, we can get that underlying, right? We can get that underlying waveform. It's a decomposition of a signal into evidently some simpler pieces. Delta functions by themselves are pretty simple. So we're getting a linear combination of delta functions as a way of decomposing the signal. Taylor, right, decomposed into different kinds of functions, polynomial pieces. Later on, when we get to transform domain, we're going to see a different kind of decomposition. Something like a Laplace transform decomposes signals in terms of complex exponentials. Fourier decomposes signals into a linear combination of sinusoids. This sifting property decomposes a function into a linear combination of shifted delta functions. Okay, I think that's probably good for the current lecture. We will pick up on these continuing Chapter 1 topics. We'll transition from signals into systems in the next lecture.